right, so example number 3 is we wish to use Simpsons rule with n equals 10 to approximate the integral from 1 to 2 of dx over x, or 1 over x dx. So the one thing we do have to remind ourselves of is with Simpsons rule, we always have to have n is even. And so remember, Simpsons rule is delta x divided by 3. And then our pattern, it always starts with 1 and ends with 1, and then it goes 4, 2, 4, 2, 4, 2, 4, 2, 4, 2 on the inside. So this leads to some interesting patterns to figure this out. All right, so let's go ahead and get started. So we identify our f of x is going to be 1 over x. Our delta x, as always, is b minus a divided by n. So in this case, it's going to be 2 minus 1 over 10, which gives us 1/10. And since we're doing decimal approximations, we can also just use 0.1. And then our x sub I is going to be a plus I times delta x. Our a is 1, our I, and then 0.1. So we get that our x sub I is equal to 1 plus 0.1 I. So then finally, we are ready to set up our Simpsons rule, right? So our partition essentially is going to look like, as I goes from 0 to 10, we're going to have the inputs 1, 1.1, 1.2, all the way until we get to 2, right? So our formula is delta x divided by 3. So we have 0.1 divided by 3 times 1 over 0.1 plus 4 times 1 over 1.1 plus 2 times 1 over 1.2 plus 4 times 1 over 1.3 plus 2 times 1 over 1.4 plus 4 times 1 over 1.5 plus 2 times 1 over 1.6 plus 4 times 1 over 1.7 plus 2 times 1 over 1.8 plus 4 times 1 over 1.9, and then finally we get back to 1. And we're going to have just one of them, and we're going to get 1 over 2. Closing our parentheses, right? So that's our Simpsons rule, writing all of this out, right? 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. So now we just need to evaluate this whole thing. So let's go ahead and type this thing in. So 0.1 divided by 3 times, and we have our parentheses 1 divided by not 0.1, that should just be 1 over 1. So 1 divided by 1 plus 1 divided, 4 times that, so 4 divided by 1.1 plus 2 divided by 1.2 plus 4 divided by 1.3 plus 2 divided by 1.4 plus 4 divided by 1.5 plus 2 divided by 1.6 plus 4 divided by 1.7 plus 2 divided by 1.8, that's not an 8, plus 4 divided by 1.9, plus finally 1 over 2. Close our parenthesis, and we get this value. So one thing we might note is we can exactly figure this out, right? Because we know what the integral from 1 to 2 of 1 over x dx is. That's the natural logarithm of the absolute value of x evaluated from 1 to 2. So that's the natural log of 2 minus the natural log of 1, and the natural logarithm of 1 is 0. So if we double check this, we can go to the natural log of 2 to compare our accuracy. So using Simpsons Rule and n equals 10, if we compare our approximation to the exact value, we'll notice that these two things match up all the way out to 4 decimal places, right? So our approximate integration using Simpsons Rule, we got all the way out to 4 decimal places of accuracy using 10 things, right? So one thing we noticed about Simpsons Rule, unlike some of the other rules, typing this in was a little bit more difficult, right? Why was that? Yeah, well, we didn't. We can, but it requires a lot more work because our pattern goes 4, 2, 4, 2, 4, 2, 4, 2, right? So there are a few different ways we can think about this. So we always have that our y of x0 plus our y of xn, we only have one of those, right? And then what do we notice? In our pattern, our next group is multiplied by 4, and when we look at our Simpsons Rule, when we have 4 in front, what do we notice about the subscript underneath? Well, 1, 3, 5, 7, it's going to be all of the odd subscripts. So we're going to have our y sub whatever, x sub n. All right, let's make it k. And in this case, k is going to be odd. So it's like 1, 3, 5, dot, dot, dot. And then we have our 2's. And our 2's are going to be our y sub, our x sub j's. And in this case, it's going to be j is even, and it is in between 2 and n minus 2. So in theory, we could write all of this out still as delta x divided by 3. We have to do our y1 of x0. Excuse me. Our y1 of xn plus 4 times our sum as k goes from 1 to something, and we need our y sub 1 is going to be x to the k, but k needs to be an odd number. So in mathematics, how do we represent odd numbers? So if we look at our thing here that we want to be odd, if we specify that k has to be equal to 2 to the n minus 1, when n is 1, what am I going to get? 1. When n is 2, what am I going to get? 2 times 2 is 4, minus 1 is 3, and so forth, right? So this is going to generate the odd numbers, but now I don't stop at n, right? Where am I going to have to stop? Yeah, what about n over 2, right? Because it's even. So we're going to stop, we're going to start, so if I write this as k goes from 1, and my x sub k has to be 2n minus 1, I'm going to stop at n over 2, plus 2 times the sum, and this time we're going to also start at k equals 1, and we're going to go to we'll figure out where we're going to stop there. We're going to do the same thing, y sub 1, x sub k, but in this case, k is going to have to be 2n, right? But we want to start at 2, so 1, and we want to stop at n minus 2, so we're going to have to stop at n minus 1 over, or n minus 2 over 2. So it makes it a little more complicated even to write it out that way. But doing this will make our life a little bit easier if you said had n equals 50. What we just did with 10 was a giant pain, right? So imagine trying to do it with 50. They're not going to make you do that in the homework. But imagine it would be a bit of a pain. So this is something that is often outsourced to a computer, right? So if you've ever done any programming, this is a great for loop, right? It's very simple to have it write a nice little simple for loop that will do this for you. So, all right, that is the end. So we want to talk about improper integrals. So until now, we've only considered integrals over a finite closed interval a to b, and f does not have an infinite discontinuity anywhere inside the set AB. So basically we're saying there's no vertical asymptotes. Well, now the question becomes, well, what if there is one? Can we still integrate this? And if so, what does it mean? All right, so those are all valid questions. So if the integral from a to t of f of x dx exists for every number t bigger than a, then we define the integral from a to positive infinity of f of x dx to be equal to the limit as t goes to infinity of the integral from a to t of f of x dx. So we're going to use limits to extend the idea of integration to an infinite set. So up until now, we've always integrated from like 3 to 5. Well, now I want to integrate from 5 to infinity. Turns out that this is really useful in a lot of applications in physics and a lot of other things because we need to allow things to go to infinity very often to sum up the entirety of something that we want. So we can do the same thing also going to negative infinity. So both of these are definitions. And the idea with these definitions is we will use this notation and the notation from the Fundamental Theorem Calculus Part 2, but we know that when we use that notation, we really mean this limit. So in this section, I will explicitly write it out using the limits, but the convention is after this section, most of the time we don't write out this. As we'll see, with, let's say, the limit from a to infinity, we know that it means the limit as t goes to infinity of the integral from a to t. So we'll just know that when we have an improper integral of the form infinity as the upper or lower limit, this shorthand notation means this formally, and then we're not going to write it. Okay. So let's go ahead and take a look at a couple of integrals. So we wish to compare the following two improper integrals. So formally, in our formal notation, we will write out the limit as t goes to infinity of the integral from 1 to t of 1 over x dx. So then we know how to calculate the antiderivative of this. So our limit comes along for the ride. The limit as t goes to infinity of the natural logarithm of the absolute value of t evaluated from 1 to t. So that's going to be the limit as t goes to infinity. Sorry. This one's an x. I'm getting too excited. That will be a t in the next step. So now I evaluated at t, so I get the natural logarithm of t minus the natural logarithm of 1, and the natural logarithm of 1 is 0. So then we get the limit as t goes to infinity of the natural logarithm of t. And note, I dropped the absolute values because my limits of integration were from 1 to positive infinity, and that's positive. So the absolute value of positive t is just t. Okay, so now what's the limit as t goes to infinity of the natural logarithm of t? Well, it diverges to positive infinity, right? Because the natural logarithm is an increasing function, and it just increases forever. So it increases very slowly, but it does increase forever. All right. Let's take a look at our second one. So this time we have the limit as t goes to infinity of the integral from 1 to t of 1 over x squared dx. So in order to do this integral, we rewrite 1 over x squared as x to the negative 2, right? So then it's power rule. So we have the limit as t goes to positive infinity of x to the negative 1 divided by negative 1, evaluated from 1 to t. So let's clean that up a little bit. So the limit as t goes to positive infinity of negative 1 over x, evaluated from 1 to t. So now finally, we can do our f of b minus our f of a. So we're going to have negative 1 over t minus a minus, so plus 1 over 1. So that's our f of b minus f of a. So now as t goes to positive infinity, what does 1 over t go to? Well, a constant divided by infinity goes to 0. So what does that limit equal? 1. Interesting. So the integral from 1 to infinity of 1 over x dx equals infinity, or it diverges. But the integral of 1 over x squared from 1 to infinity is equal to 1. That's interesting. So what does that tell us about the curve 1 over x? So if this is 1 and this is 1, so we have something that looks like this, and we integrated from 1 to infinity. It says that the area underneath that curve between 1 and infinity is equal to what? 1. Right? For this curve, and if we did our other curve, 1 over x, it has infinite area underneath it, right? It went to positive infinity. Seems a little counterintuitive. So remember, ordinal numbers don't behave the same as other ones, but in this case we get 1, and in the other case we get positive infinity. All right. Let's take a look at example number 2. We have the integral from negative infinity to 0 of x cubed e to the x. So formally, this is going to be the limit as t goes to negative infinity of the integral from t to 0 of x cubed e to the x dx. So how are we going to find the antiderivative of this? Super long way is integration by parts 3 times. The nice way is tabular integration. So we make our table, and we have our x cubed, and we have our e to the x. So we differentiate down the left side. So that gives us 3x squared, 6x, 6, and 0. And then we're going to integrate down this side, so that's just e to the x, e to the x, e to the x, e to the x. And then we have to make every other term negative, because when we do integration by parts, it's uv minus the integral of v du. So that minus sign comes from the by parts. And then we connect the diagonals. So we get then the limit as t goes to negative infinity of x cubed e to the x minus 3x squared e to the x plus 6x e to the x minus 6 e to the x. And we need to evaluate that from t to 0. So the first thing I'm going to do is factor this, because I have a common factor of e to the x in all of them. So I have x cubed minus 3x squared plus 6x minus 6 times e to the x. And I'm going to evaluate that from t to 0. So I have the limit as t goes to negative infinity. When I plug in 0, I'm going to get 0 cubed minus 3 times 0 plus 6 times 0 minus 6 times e to the 0 minus, when I plug in t, I get t cubed minus 3t squared plus 6t minus 6 times e to the t. Well, that first part, I have a whole bunch of things that are equal to 0. So they're going to just go to 0. And the only thing that's left is the negative 6 times e to the 0. And e to the 0 is 1. So that's negative 6 minus t cubed minus 3t squared plus 6t minus 6 times e to the t. So now we got to take a trip down memory lane in our way back machine. How am I going to evaluate that limit? Well, if I look at the limit part, negative infinity cubed is negative infinity. So the polynomial part goes to negative infinity. And what does e to the negative infinity equal? 0, right? And remember, we can't just say infinity times 0 is 0. So what was the rule we learned in Calc 1 that helped us figure out infinity times 0? What's that? Yeah, L'Hopital's rule, or as some people like to say, the El Hospital rule, right? So L'Hopital's rule is how we're going to resolve this. So by L'Hopital's rule, we're going to rewrite this as t cubed minus 3t squared plus 6t minus 6 over e to the negative t. Then it's going to be type, as t goes to negative infinity, it's going to be type infinity over infinity. And so what is it that L'Hopital's rule tells us we can do? We take the derivative of both the numerator and the denominator, but not using the quotient rule, just independently. So by LH, we're going to get 3t squared minus 6t plus 6 over negative e to the negative t. So we take the derivative of each. But if we go to negative infinity again, the numerator is still negative infinity, and the denominator is still infinity. So we get another type, infinity over infinity. So we actually end up having to use it a total of 3 times. So we're going to do L'Hopital's again, and L'Hopital's a third time. So the second time is going to yield 6t minus 6 over e to the negative t. And then by L'Hopital's again, we're going to get the limit as t goes to negative infinity of 6 over negative e to the negative t. So now finally, this is going to be a constant over infinity. And a constant divided by infinity finally tells us that the limit is going to be 0. Whew. So after all of that work, we've just determined that this limit is 0, essentially by L'Hopital's rule 3 times. So then what does our limit equal? What was the only thing that wasn't 0? Negative 6, right? So this guy right here was the only thing left. So then the integral from negative infinity to 0 of x cubed e to the x dx is equal to negative 6. Interesting, right? So let's recap a little bit what happened there. So we did our integration by parts using tabular integration, and we ended up with an indeterminate form of type infinity over infinity after playing with the algebra a little bit. And then we applied L'Hopital's rule 3 times to find that that was equal to 0. And then that gave us the value of that integral is negative 6. All right, so let's talk about this integral a little bit. So it was doubly infinite, and that might have thrown us for a loop a little bit. But let's analyze this a little bit. So if I look at my integrand, I'm just going to call it f of x. we have 1 over x squared plus 1. So one thing we might notice is that the interval of integration is from negative infinity to positive infinity. Well, the interval is symmetric. And we'll notice something else. With our function f, if I replace x with negative x, I get 1 over negative x squared plus 1, which is 1 over x squared plus 1. So the interval is symmetric, and if f of negative x equals f of x, and f of x is an even function. And our property for that is, if we have an integral of an even function on a symmetric interval, it's equal to twice the amount from 0 to one of the things. So ours is going to be the same as 2 times the integral from 0 to infinity of 1 over x squared plus 1 dx. So one thing I do want to note, you don't have to do it this way. If you just evaluate it, you're going to get the same thing. What is the antiderivative of 1 over x squared plus 1? Should be inverse tangent, right? And if I evaluate that from 0 to infinity, it's going to be 2 times. And what's the inverse tangent of infinity? Or said the proper way, what's the limit as x goes to infinity of the inverse tangent of x? It's the horizontal asymptote of the inverse tangent function. Let's ask it another way. What's the vertical asymptote of the regular tangent function? So where does the tangent function go straight up and down? Not at 0. Tangent of 0 is 0, right? So let's see. Tangent by definition is sine divided by cosine. So it's going to have a vertical asymptote whenever cosine is equal to 0. When does cosine equal 0? Well, cosine is x on our unit circle. So when you're on the y-axis, so it's going to be pi over 2. So the inverse tangent of infinity is pi over 2 minus the inverse tangent of 0 is 0. So we get pi. So notice this time I didn't use the formal notation. We wrote it out just like we would the good old fundamental theorem of calculus. We know infinity is not a number, and we know we're taking limits, but we'll write it out as if it were a number. So, as I said, this isn't the formal notation, but this is how every calculus book is going to write this. So when people write this, they do that whole limit thing for about 10 minutes in this section, and then it disappears, and we use this notation, knowing that it means the limits when we're going to infinity. So it's worth noting, if you didn't do the whole even function thing, we still have that the antiderivative is inverse tangent of x, right? So essentially it's going to be the inverse tangent of infinity minus the inverse tangent of negative infinity. Well, we already knew that this one is pi over 2 minus the other horizontal asymptote or vertical asymptote of tangent is negative pi over 2. Because its domain is from negative pi over 2 to pi over 2. Add those up and you get the same thing, right? So, like I said, the symmetric even function thing is helpful, and we'll see some other occasions to use it in this section. But as always, it just saves you a little work. It doesn't actually make you be able to do a problem you wouldn't be able to do otherwise. All right. Our next example is for what values of p does this integral converge? All right, well, let's go ahead and do this integral. I'll be a little more formal this time, so let's set up our limit as t goes to infinity of the integral from 1 to t of 1 over x to the p dx. So, first observation, we know from example 1 that p can't be 1. Because if p is 1, you get this integral, right? And what did we determine that that was? Infinity, so it diverged. So from example 1, we know p cannot be 1. Well, that's good, because that's the one exception to that rule. So in order to do this integral, then, we're going to use the power rule. So we have the integral from 1 to t of x to the negative p dx. And we have the limit as t goes to infinity. We add 1 to our exponent and divide by it. So we have x to the negative p plus 1 divided by negative p plus 1. Because that's our power rule. You add 1 to the exponent and you divide by it. Like if it was negative 2, it would be negative 2 plus 1 divided by negative 2 plus 1, right? Okay, and then we are going to evaluate this from 1 to t. So that's going to give us the limit as t goes to infinity I'm going to factor out the 1 minus p, though. 1 over 1 minus p times the limit as t goes to infinity of t to the negative p plus 1 minus 1 to the negative p plus 1, right? We just plugged in our t and our 1, so f of b minus f of a, and I pulled the p, the negative p plus 1 out in front as 1 over 1 minus p. So now we need to evaluate this limit. So the second one right here, what is 1 raised to any power going to be? Just 1. Because 1, no matter what its exponent is always 1. So that's not what we're going to have to worry about. We've got this guy right here. So we have the limit as t goes to infinity of t to the negative p plus 1 minus 1. So remember, our question is, for what values of p does this integral converge? So from Calc 1, we know that the limit as x goes to infinity of 1 over x to the c converges when c is bigger than 0. So what this tells us is that it has to be in the denominator and bigger than 0. Well, ours isn't in the denominator. So to move an exponent from the numerator to denominator, what has to be true about it? It has to be what? Yeah, it has to be negative, right? Because if I have x to the negative 3, what is that the same as? 1 over x cubed, where 3 is a positive number, right? So what would have to be true about negative p minus 1 then? If we want to move it from the numerator into the denominator, since it's already in the numerator, it would have to be negative. So we want negative p plus 1 to be less than or equal to 0. So we add p, and that tells us that p has to be strictly bigger than 1. So the integral will converge when p is greater than 1. So as long as that exponent is bigger than the number 1, it will converge. All right, so now we want to talk about the other type of improper integral. So in the first two examples, or the first few examples, we let x go to positive or negative infinity. This time, if f is continuous on a half open interval and is discontinuous at b, we can then extend the definition of the integral from a to b of f of x to be the one-sided limit as t approaches b from the left of the integral from a to t of f of x dx. And similarly, if it's discontinuous at a, we can then approach a from the right while staying in the interval ab, right? So these are our two definitions to expand integration to where a function is discontinuous at an endpoint. All right, so this time we'll notice, where is our function discontinuous? At 2, right? So we want to integrate from 2 to 5, but can I actually put the value of 2 into this function? No, because if I put 2 in, 2 minus 2 is 0. I'm dividing by 0, and that's undefined. So we formally define our integral as the limit as t approaches, and since I'm on the interval from 2 to 5, and I'm integrating this part, when I approach 2, I'm going to be approaching 2 from the right side, so I approach 2 from the right of the integral from t to 5 of 1 over the square root of x minus 2 dx. So to do this integral, I'm going to need to do a U-substitution. So U is going to be equal to x minus 2. Then du is going to be equal to dx. So we get our integral. We're going to have 1 over the square root of u times du, which is going to be the integral of u to the negative 1/2 du. So we add 1 to our exponent and divide by it. So we get u to the 1/2 divided by 1/2. So that's going to be this 2 times the square root of u. Because if we make u a fraction over 1, we multiply by the reciprocal, and u to the 1/2 is the square root of u. So finally, after doing that limit, we get the limit as t goes to 2 from the right of 2 times the square root of u, and u is x minus 2. And we're going to evaluate that from t to 5. So we have the limit as t approaches 2 from the right of 2 times the square root of 5 minus 2 minus 2 times the square root of t minus 2. So our first piece, 5 minus 2 is 3, so we get 2 square roots of 3 minus 2, but then we approach 2 from the right. 2 minus 2 is 0, so minus 2 times the square root of 0. So we get 2 times the square root of 3. So one thing to note, up until this point, I've strongly encouraged you always to change your limits when we do a U-substitution. You can do it when we have improper integrals, and I'll go through it right now, but I think it tends to make things less clear as opposed to more clear. I will illustrate the process, and if you like it, by all means use it. But if not, when we went back to this stage right here, when we changed, so to change the limits of integration, let's see what we had. We had square root of u du, and we had u equals x minus 2. And our limits of integration were originally from t to 5. So u of t is going to be t minus 2, and u of 5 is going to be 5 minus 2, which is 3. Okay. So that gives us this. With our new limits of integration, that part's not so bad. This is where we have to be very careful. There was one more piece that we didn't have to worry about before, which was the limit. So how are we going to deal with the fact that t is approaching 2 from the right? This is why I don't like to deal with these, and I just do the substitution and substitute back out. It can be done, and let's talk about how we do it. So if we do the substitution u equals x minus 2, we're basically asking the question, if we have the limit as t approaches 2 from the right, we've got this expression. So what is the limit as t approaches 2 from the right of our u of t? Well, u of t is t minus 2. Well, that's going to be the same. What does u approach when we put 2 in? Well, what's 2 minus 2? 0. So this is the same as the limit as u approaches 0 from the right. Because we're transforming the limit from the input variable t to the output variable u. So the limit as t goes to 2 from the right of u of t goes to 0 from the right. So the limit as u approaches 0 from the right of u. I know, it's a little interesting. But now we know what the antiderivative was. It was 2 times the square root of u. So if we have the limit as u goes to 0 from the right of 2 square roots of u evaluated from each of these, so this is now u, from u to 3, we have 2 times the square root of 3 minus 2 times the square root of u. When we take that limit, this is 0, and we get 2 square roots of 3 again. I feel like that is a lot more complicated. Like I said, it can be done, but I wouldn't lose any sleep over trying to do it that way. It's a lot easier just to back substitute, and after you've had time to let this sink in, come back and think about it, and it'll make a lot more sense. So I want to mention it, put it out in the universe, but not recommend that that's the method that we're going to use. All right, so the next one is for you guys, and